Hey everyone, welcome back to Chips and Salsa, where we talk security at Intel. I'm Jerry Bryant, your host. Today's topic is software robustness, the role of hardware in that, and I'm most excited about new technology coming to the x86 ecosystem, which we'll get to. I'm joined by three of my brilliant colleagues here at Intel. Can we start by you guys giving us all a introduction of yourselves and how your roles relate to software robustness?
I'm Michael LeMay. I'm a principal engineer and CPU architect. A couple examples of existing x86 processor security technologies that have contributed to our control flow enforcement technology and virtualization technology redirect protection. My current focus is memory safety, which is an area I've been working in for over a decade.
My name is Joe Sahula, and I'm a senior principal engineer in Intel's Software and AI group. I'm one of the original architects of Intel's trusted execution technology, and I've contributed to a variety of security technologies from the XD-bit to Intel trusted domain extensions, My current projects include memory safety and confidential computing.
Nice.
And I'm Esma Mahasni. I lead the software robustness pillar, driving Intel's full stack approach from silicon to ecosystem. I am a system architect and principal engineer with background in systems, high-performance computing, and platform security. And I recently led the confidential AI architecture and continue to engage with industry on securing AI.
Awesome. Well, welcome everyone. So let's get started here. When we say software robustness in the context of modern silicon and platforms, what do we actually mean? And how is it different from just security or reliability?
It comes down to recognizing that software is imperfect. Even AI-generated software is far from perfect. In fact, some studies show a relatively larger number of bugs in AI-generated code. Software imperfections create chinks in the armor of a system's security that hackers can exploit. Our job is to keep the hackers out, even when software isn't perfect.
So software robustness is also about how the software handles unusual conditions, even when such conditions don't include the security aspects like Michael talked about. And a key to gracefully handling these conditions is knowing that your software is going to still have integrity and can still be relied upon to make decisions and execute them to handle these conditions.
When we say software robustness, we're talking about how the system behaves when things go wrong. Not if, but when. It's a full stack coverage, starting from hardware protections in silicon, isolation and containment in runtime, as well as compilers doing checks and structural checks, and as well as sanitizers and memory safe languages. Robustness is really a mindset that says we assume a failure will happen, and we architect the system so that when it does, we see it, we understand it, and we move forward without compromising safety, performance, or user trust.
So why has software robustness become such a critical priority in recent years? I mean, what trends and workloads, the threat landscape, or hardware capabilities are driving this focus?
Yeah, industry and academia have been wrestling with this for several decades. So there's been a back and forth between growth and software complexity, connectivity, and criticality that's increased exposure versus important progress that we've made with exploit mitigations in hardware and software. However, targeted exploit mitigations are hitting their limits. We now need to strike at the root of the problem by focusing on the software bugs that hackers use as their initial entry point.
Robustness has been an issue ever since there was software. But now that software is running the most critical aspects of our lives, from the utilities providing electricity and water, to the data centers doing the e-commerce, and even to the TVs and appliances in our homes, if these fail or they're attacked, it could result in everything from physical damage to stopping business. So when combined with a shift from hackers doing it for fun to doing it for profit or for national security, the consequences are just so much higher today than they used to be.
Look, the old problem is memory safety. The new problem is AI agents have memory. They hold credentials, they chain tools, they act autonomously. So if there is a single corrupted input, that doesn't crash the system. It quietly changes what the agent believes and does. That's why hardening infrastructure is more important than ever. It ensures that when something goes wrong, it's visible, fast, and contained.
So what are some of the most common ways software robustness breaks down in practice, especially in like low level or performance critical code? What kinds of real world issues can that lead to?
Yeah, security exploits of low-level code are some of the most severe, given the high level of access that code typically has. For example, they may allow taking over a system silently, which bypasses traditional defenses against phishing and malware and so forth. Organized crime and state-sponsored groups often pay millions of dollars for such exploits to be deployed against high-value targets such as journalists, government officials, activists, and ransomware targets.
And as I noted earlier, software runs all of our utilities, such as electrical generation and transmission. So a bug or an attack could disrupt electricity for millions of people, businesses and critical services like police and hospitals. So not only can these low-level attacks bypass the defenses, like Michael noted, but they're also so much harder to fix because these low-level defenses also control the mechanisms that would normally be used to update the software and make those fixes.
So historically, robustness has often been viewed as a software-only responsibility. How does the role of hardware and microarchitecture, how has that evolved to actively support more robust software?
Yeah, focused hardware enhancements can have a disproportionate effect on the level of security and efficiency that's achievable for defending against a given type of security threat. And we've already seen this dynamic play out for defenses against stack smashing. Software could efficiently check stack canaries, for example, but those were sitting exposed in program's memory. And so they were easily bypassed. Introducing hardware shadow stack protections as part of Intel Control Flow Enforcement Technology, or CET, in 2020 was a major step up in hardening. Virtualization Technology Redirect Protection, or VTRP, is another example which avoided the significant overheads from software-only protections against rootkits.
There are other cases where it's not even feasible to prevent attacks with software, such as cold boot attacks where memory contents are extracted from the DIMMs themselves, or DMA attacks that are launched from devices like PCI Leech. In these cases, hardware is really the only way to efficiently provide the protections necessary to prevent them, by encrypting memory or by filtering the DMA accesses, respectively, for those two attacks.
So from a developer's perspective, what are the key trade-offs when adopting robustness features? Performance, complexity, tooling. How is Intel helping to reduce that friction?
Well, I think you can fit all of the trade-offs that you mentioned into those three categories. Solutions that aren't performant either won't be used or will have the protections turned off. And so Intel does extensive benchmarking and analysis to ensure that our solutions will be usable by the ecosystem. The principle of Occam's razor, that the simplest solution is usually the best, also applies to software robustness. So, as Michael said at the beginning, we look for the root of the problem and try to address it there because that often leads to the simplest overall solution. And for the last category of tooling, Intel tries to make the developer's job as easy as possible by pushing the complexity and work into our hardware and into the compilers and other tools that the developers use to build their software.
Okay, just to amplify Joe's point about the efficiency of Intel robustness features, something top of mind for everyone today is how to make the most of available memory. Intel CET and VTRP are both great examples of existing memory-efficient security hardening technologies. Memory overheads have also been a crucial challenge for memory safety hardening up until now, and we're excited to finally have a solution for that, as we're going to share more about later in the episode.
Many robustness issues ultimately tie back to memory safety. Can you talk about why memory safety is such a persistent challenge and how that led the industry toward approaches like memory tagging technology that we're going to talk about right now?
Sure. So the industry has tried many approaches to addressing memory safety, from static analysis tools to software-based checking to runtime monitoring. None of these have satisfied the trade-offs that we just discussed. Even memory-safe languages have their limitations.
Yeah, low-level programming languages such as C and C++ give developers a lot of control over how memory is managed and accessed. That's very powerful, but it also magnifies the risks of software bugs. Around 70% of software vulnerabilities are due to memory safety issues. Just like racetracks are lined with tires, the industry needs guardrails around these powerful programming languages to enforce safety without hindering performance excessively. Memory tagging technology provides those guardrails.
For viewers who may be new to it, how would you explain memory tagging in simple terms, and how does memory tagging technology, or MTT, relate to that?
Though processors today see memory as a huge flat space with no clear boundaries between objects and no sense of what objects are still valid, so hackers exploit that to perform invalid memory accesses, leading to security compromises. And bugs can trample memory and cause crashes. Memory tagging makes object layouts and lifetimes visible by comparing tags in pointers with tags associated with specific memory locations being accessed. So via these comparisons, the CPU can immediately detect invalid accesses. If a pointer is used to access a memory object with a different tag, for example, due to a buffer overflow or a use after free error, the hardware identifies the mismatch and halts the operation, preventing the most common memory safety vulnerabilities. So Intel invented memory tagging technology as a set of instruction enhancements and additions to accelerate tag checking in hardware.
So we've had software-only solutions for memory safety for years. What advantages does hardware-assisted memory tagging bring compared to those approaches?
Well, software solutions such as address sanitizer or ASAN and Valgrind, they require large amounts of memory and are too slow for use in production environments. And because they can only be used for testing, if no test case has just the right sequence of events or exactly the right timing, then these may not actually catch some of the vulnerabilities in the code. Since MTT is implemented in hardware, it requires less memory, uses hardware-accelerated instructions to perform the checks, and so it is fast enough to use in production environments, and so it always protects the software.
Performance, it's always a concern. How do you think about performance and memory overhead of MTT, and what kinds of workloads are good candidates for enabling it?
While architecting MTT, we've been very intentional about putting the control in developers' hands for where to set and check tags. MTT is a pay-as-you-go approach, which avoids the memory overheads of ARM MTE and Apple MIE that require reserving a fixed amount of physical memory up front. MTT also avoids increasing the sizes of pointers, which is a significant source of overhead for ARM Cherry. MTT has instruction granular controls, which allows compiler optimizations and the increasing use of memory-safe languages to reduce tag checking performance overheads while still enforcing memory safety throughout the system.
Is MTT an Intel-only technology?
Well, let me start by saying that in October of 2024, Intel and AMD formed the x86 Ecosystem Advisor Group, or EAG as we call it, to collaborate on architectural interoperability and simplify software development across the x86 ecosystem. And although Intel invented MTT, which we called CheckTag originally, we have brought it to the EAG, where our two companies, Intel and AMD, and other members of the x86 ecosystem are creating a unified specification. And this is what we first announced in a blog last year in October.
And we'll put a link below for that. So Esma, maybe this is a question for you. MTT is not just a CPU feature. It depends on the broader ecosystem. So what's required across compilers, runtimes, operating systems, and firmware to make memory tagging technology effective?
Yeah, so memory tagging delivers maximum value when the entire stack supports it. So the OS must enable and handle tags and faults correctly. Compilers instrument code with tag checking operations while maintaining compatibility. So existing or legacy hardware ignores the instrumentation, which allows for a single binary to be generated. At runtime, hardware-supported address masking preserves tagged pointers, which is across library calls and system boundaries, which is actually a big advantage over software-only approaches. Debuggers and monitoring tools also need to understand MTT and make faults actionable. I think about this through what we are calling the deployability lens. Can you turn on memory tagging in production without major application rewrites or fragmenting your fleet? The answer has to be absolutely yes. The silicon gives you the foundation. And with the full stack designed and architected to support it, that's how you get memory tagging to become a default part of how serious x86 systems are built and run.
Awesome.
Yeah, and we have carefully architected MTT to operate at all levels of the system, from UEFI firmware up through hypervisors, kernels, and applications.
The Ecosystem Advisory Group that I mentioned in the previous comment also includes companies from all parts of the ecosystem, including operating system vendors, tool vendors, major software developers, and cloud service providers. So this diverse membership is what helps to ensure that the technologies like MTT that are going through the EAG are not only effective for a broad set of usages, but will also have the support of all of these needed ecosystem elements and partners.
So what are some of the most compelling use cases for MTT, whether today or in the near term? And are there any particular domains or workloads where you expect it to be adopted first?
Absolutely, and use cases are important. I would say some of the most compelling near-term use cases are environments where memory safety risk is high and performance still matters. Think about large services, system software, security-sensitive workloads. Think about big C and C++ code bases processing untrusted data from browsers, load balancers, storage systems. These systems can't simply be rewritten in a safe language, and they cannot afford the instability. In cloud and data center environments, for example, you have fleets that are running at massive x86 scale. MTT brings hardware-accelerated memory safety directly to the workloads, hosting your highest value and multi-tenant services. It's not a silver bullet, but for large x86 deployments that can't move to memory-safe languages overnight, MTT is a practical way to raise the security bar without giving up the performance and ecosystem that they depend on.
If I'm a developer or software vendor, what changes, if any, do I need to make to take advantage of MTT? And how do you envision the ideal developer experience?
That's an important one, and I know we all spend a lot of time thinking about developers. Aiming for a push-button developer experience by shifting the complexity away from developers and into the hardware compilers and other tools so we can simplify and ease the adoption. Ideally, you get the robustness benefits without having to rewrite your application or re-architect your code. The goal is also incremental adoption. You build with MTT-aware tool chains, enable it in your most security-critical components first, and then expand from there. And for example, when tagging catches a memory error, you get clear, actionable diagnostics instead of mysterious crashes.
Nice. So for teams that want to improve robustness today and prepare for MTT and related technologies, what practical first steps would you recommend?
Absolutely. So for those that want to get ahead, I would say there are three things, or focus on three areas. First, understand your current memory safety exposure. Where are the vulnerabilities that matter most in your environment? Use existing sanitizers and fuzzing to reduce latent memory errors right now. The fewer the bugs in the system, the smoother the MTT transition is going to be. Second, think about deployability, not just capability. Plan where you would enable MTT when it comes, especially security critical services that are tied deeply to x86 infrastructure. And third, engage with us on use cases. We're actively shaping and defining where these deployments are going to be, and feedback and engagement from researchers, from developers, as well as our customers is very critical and shapes this work. If this is relevant to your environment, we want to hear from you.
If there's one key message you'd like to leave our viewers with, what would that be?
I'll start. One thing to add is we're seeing a real shift in industry. When it comes to memory tagging and MTT, the question is no longer, is this feasible or do I need it? It's how do I operationalize and deploy this? I think that's a very healthy shift, and it's exactly the conversation we want to have with the ecosystem.
MTT is just one more example of how Intel's driving the x86 ecosystem to be the most secure, most compatible environment in which to run all of your workloads, from business critical to personal computing.
Yeah, and Intel is incredibly dedicated to the robustness of all software, which is evident from our track record of existing technologies and why we are now architecting MTT to give developers an unprecedented level of control over memory safety checking.
Well, okay, so this is great information. I want to thank you all for joining me here today to talk about this very important topic. For those interested in learning more, you can check it out in our 2026 Intel Platform Security Report, which you can find at intel.com/security report. Thanks for watching.